reactive power control under the voltage write-through period, we use LP card and LQ card. Let's see the LQ card first. LQ card means LQ card means the reactive power control, and you can see it includes many control modes. For example, for the for this parameter, you can write 0, 2, 3 to change the the reactive power control mode. For example, if you write 0 in this parameter, it means we use the voltage to control reactive current. Means the more voltage drop and the more reactive current the DFIG output to support the voltage. If you write, for example, if you write 3, it means you give a certain reactive value. And you can see if this parameter you write 0 in this parameter, the reference, the voltage reference value means the limit to start the gate to start the voltage write through control. It writes 0.9 means when the voltage drop below 0.9 and the write through control start to work. And another important parameter is the reactive power adjustment coefficient. This this these parameters corresponding to this sorry to these equations. K means the coefficient, and 0.9 means the gate, and the US means the voltage of the DFIG when fault occurs. IN means the rated current. So that is how much the reactive reactive current is after it going through the voltage right through control right through period. For the active power control, you can see there are so many parameters. Let's see the sample. In this sample, the LQ card, the new 30 is a DFIG, and the LQ card is reactive power control system. In this parameter, I write 0 means the output of reactive power depending on the voltage, and the gate I write 0.9. The coefficient write 1.5. So if the voltage of the DFIG drop to 0.5, the output reactive current is this number. This number multiply 0.9 negative the 0.5 and multiply the rated current. Okay. The write through state judgment, we used EV card. to describe this. The control mode of grid side inverter compared with rotor side inverter. Grid side inverter control system is very easy. We use EU card to describe it. We also have voltage ride-through protection model. It contains crowbar and chopper. They are very common protection devices in DFIG. The crowbar means the turbine side converter being bypassed, so the current won't 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 be too big. And the chopper means connect a resistor in parallel on the DC bus to share the voltage burden of inverter. We use MR card to model the crowbar and the chopper. It contains all the detail, all the parameters in detail. Next is a pitch angle control model, and it's very simple. Frequency control model. We use EY, and we also consider the power speed curve. The output power and the wind speed, they have a relationship. So we have card to fill in a lot of power speed points in the power speed curve. The program read the corresponding bit speed from the curve based on actual power value to simulate the power under different wind speed. Okay, next is a direct drive wind turbine model. The the model, most important part of this model is grid side converter. The grid side converter adopts grid voltage oriented vector control. Assuming the voltage amplitude of grid node is U1, the power injected into grid by the grid side converter is these equations. You can see there are a lot of cars to model to describe the direct drive wind turbine model, but only the mechanical part is different from DFIG. The control part, the active and reactive power control, frequency control, and the ride-through and any control under ride-through period, they are same as the DFIG. The logo of direct drive wind turbine in the DSP is MY card. If I see the first line of the devices is MY card, I know it is a direct drive wind turbine. It includes 10 cars. 8 cars are required mandatory, and 2 cars are optional. Wind turbine model calculate the mechanical power input by the wind turbine according to the change of information such as wind speed, speed of pitch angle, and fixed information such as density of air and blade radius is same as the DFIG, totally same. And this is the generator model. This is rotor. We use which card? We use MY card to describe the mechanical part, the rotation equations of the wind turbine. It contains rated capacity of wind turbine, initial voltage of DC side capacitor of the inverter, and so on. Turbine side converter model. The function of turbine side converter is to control the torque of generator During the variable speed operation stage of the unit, the speed of generator is adjusted to change with the wind speed, achieving maximum power tracking. During the constant speed operation stage of unit, it's necessary to maintain the rated speed of motor unchanged. This is outer loop control and inner loop control. The control principle. The control goal of the gray side converter is to maintain the stability of DC side bus capacitor voltage so that the active power on DC side is immediately transmitted to the grid. The second is to achieve the grid side power factor adjustment or control of reactive power, similar to the DFIG. The active power control in the normal state, it uses the same card EU as DFIG. For the reactive power control and the ride-through control, they are the same. For the protection part, it's just a little bit different. The next part is solar and energy storage model. This part is the battery, DC to DC inverter, DC to AC converter, and a maximum power point tracking, and a connection to the grid control, AC power grid. So the most important part of this system is DC to AC converter. The solar the solar system converts solar energy into direct current, fit the voltage current relationship curve based on external characteristics of a solar system. For the and and as you know, the control part, this solar part, this solar system is very easy, and for the control part, active and reactive power control and the ride-through control, they are same as DFIG. For the energy storage, for the energy storage, the key to modeling is inverter, and the energy storage is much easier. The logo for the solar and the energy storage, the logo for the solar system is MS card, and for the energy storage is BS card. For them, there are 8 cards, and 7 are mandatory, and 1 card is optional. Frequency control card is EY card is optional, and you can see the solar and the energy storage. They just have this card is these 2 cards, MS and BS card, they are different, and all other things are same. This is the equation about the solar system. This is MS card. It concludes the rated capacity of a single solar system. Open circuit voltage, short circuit current, the voltage and the current at the maximum power point, and the number of the battery. This is a capacitance. It contains all these parameters. And this is the maximum power control of the solar system. The T means temperature. The X, the X curve, the X axis means the voltage, and the Y axis P means the active power output. So you can see we get we get the relationship between the voltage and the reactive power output. So we connect the the top of all of curves to draw a new curve. It it represents we can get the maximum power under different temperature. For the solar system, it is also like this. S means the light intensities, means how strong the solar is. For the energy storage system, we have this BS card. It contains these parameters, and it is the circuit and the equations. Grid connection, control, and other mode. It is same as the DFIG. For example, I write this part from the first line, from the first card, we can see it is DFIG because the first card is card, and these are mandatory, and these are optional card. You can write this, or you cannot write this. Both okay. For this part is MY card. You can see it's a direct drive turbine. For this is MS card, solar system, BS card, energy storage. There are some example. We give some example parameters. Okay, let's check the sample first. In the sample, there is a folder named New Energy. I use the IEEE system. I remove 2 generators and input 1 DFIG and 1 solar system inside. So that's how it looks. In the DAT file, it contains the topology of the whole system. It tell us the B card means the node, and the L card means the line. The T card means transformer. So we have DAT card. We know what the topology is look like, what the system look like. And it contains some basic parameters of line, node, and the transformer. For the other part, in the SWI file, it contains the other parameters of devices. M and MF means the generator, synchronous generator. It means the node named new 32 and 2 new 39. They are all generator. And this part, MF to LQ, this part is the FIG because it has card, and it contains a lot of card, and you can select the view and a property to see the detail of the parameter. But if you can't understand how to write and how to fill the parameter, you can go back to see the PPT, PowerPoint. The table I put on the PowerPoint is more detailed. And this part is the solar system. Because the solar system is much is more simple than the DFIG, so it contains less card. Now, Now I will do some transient simulation. LS card. LS card means the fault I set. It means in the line new 2 to new 3, there's a line. I set the three-phase short circuit fault in the on the 10 cycle, and this fault is disappear, and I cancel this fault on the 15 cycle. The line is is this line, this line, yeah, this line, new 2 and new 3, and this card OMW, OMM, OMS means I want to see. It means the output choose. OMW, OMM means the DFIG output. I can change the parameter to see the variable I want to see about the DFIG. For this part, it is all the output part. The B means the node I want to output. If I want to see the current output from the new 5 node, I have to write this line. And you can see, you can change to different value to change the variable you want to see. It will give you the curve of the variable after simulation. This part is generator I want to see. In this, I put all the node in there. And before we do the simulation, we should do the power flow calculation first. Okay. Then I will do the simulation. This simulation is on the line new 2 to new 3. I set a 3-phase short circuit current, a short circuit fault. Okay, because the system is too small, so the simulation is very fast. We use the CSG chart tool to see the final curve. You can see the voltage, current, active and reactive power, and so on. For example, we see the active power output by DFIG. The curve is like this. At this time, the fault occurs and the active power drops to 0. After that, it has 2 stages of restorage, get back to normal, and the system is stable after the fault disappear. For the Q, for the reactive power output from the DFIG, you can see SI in the reactive power control card, LQ card, File, then you can do a powerful calculation. And then after you after you have you write a SWI file and you set a fault, then you can do simulate. It's it's quite a useful. Last part I want to introduce is short circuit current calculation. It's another useful function we use in the particular work. DSP offers a complete and accurate solution to short circuit calculations in three-phase AC system using this IEC 60909. it's an international standard. You can enter equipment data and the parameter, and the result meet requirement of international standard and match this. This is this is the picture of the international standard. In DSP, we can we can calculate four types of short circuit: three phase, two phase ground, one phase ground. You can get this information in the short circuit current, peak current, breaking current, and the DC component and steady state short circuit current. DSP use the equivalent voltage control voltage source at the short circuit location, symmetrical components impedance network, and the voltage factor C. The short circuit impedance for electrical equipment are modified using the impedance corrections factor. This 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 all are about the features of this function. In the calculation function, we have these assumptions. Although these assumptions are not strictly true for power system, they can give results with generally acceptable accuracy. When calculating the short circuit current of multi-voltage level system, the impedance value must be reduced from one voltage level to another. The impedance of the equipment in the higher and or secondary grade shall be divided by or multiplied by the square of the rated transformer ratio, and the voltage and the current shall be converted according to the rated transformer ratio. This is a calculation principle. And this part is principle and calculation. It is how it do the calculation, the principle of the calculation. The principle of the short circuit current and DC component. The total short circuit current includes the AC component and DC component. The AC component is generated by the action of power source, and its amplitude is related to the size of the power source and the size of system impedance, which remains unchanged during the transient process. The DC component is generated due to the inability of current in the inductive component to suddenly change, and will gradually decay to zero. The decay time constant depends on the inductance resistance ratio in the short circuit current. You can see this small circuit because we have inductive component. So after the switch open and the line is cut off, the current flowing through this branch won't change suddenly after the switch action. So the equation, we can see the equation of the short circuit current. It includes the AC part and DC part. In the AC part, only the IK is unknown because when we calculate the short circuit current, we calculate the maximum one. So the sine part is 1. The degree is 90 degree. So we have to calculate the AK part, the AK parameter. For the DC part, the IK we solved Then the only unknown variable is tau DC. Tau DC is L divided by R. It's a we use we call this decay time constant. It described how fast the DC component, the DC current drops. In this curve, it's short circuit current curve. And you can see this line is a DC current, DC component. And it won't change suddenly. It will decay time by time and until it drops to zero finally. And this is AC part. It won't change. So AC part plus DC part, it is the short circuit current. How to calculate the AC current? The AC component of short circuit current adopts the method named equivalent voltage source. The fault current. Use this equation to calculate. In this equation, C means voltage coefficient. VFO means the voltage, the rated voltage of this node, of the node we want to calculate. We set the fault. ZFF, the ZFF means the self-impedance of this node. So the AC current amplitude is very easy to calculate. We just to create the impedance matrix of the whole system. Then we will know the self-impedance of any node. And we know the voltage, the rated voltage of every node. So the current, the short circuit current of each node can be calculated. The self-impedance means when we look into the system from this node, how big is the impedance? We call it self-impedance. The voltage of any node in the network, we use this equation to calculate. G means the collection of the source node. Zij means the mature impedance between node I and J. Ij means the injection current of the source node J. Many consist of generator, motor, and so on. So if we want to calculate the AC current amplitude, the first, we need to create the impedance matrix of the whole system. And then we use the voltage divided by the self-impedance. We can get the short circuit current. And we use this equation because we have the impedance matrix first. Then we know the mutual impedance between any node. And we can know after the fault occurs, the voltage of any node. This is a table, shows what the value of the self-impedance is. Because when the fault is asymmetric, and so the ZFF is different. Z1 means the positive sequence component of self-impedance. Z2 means the negative sequence component of self-impedance. Z0 means the zero sequence. So we need to create the positive, negative, and zero sequence component of the self-impedance, and then we can calculate the current under under this type of fault. Always, we just in engineering, we only calculate the three-phase short circuit and a single phase. Next, how do we calculate the decay time constant? If I want to write the equation of this circuit. This is the fault location, and it has two branches. So the fault current comes from two branches. So we can see the decay time constant of DC component in this current has two independent time constant. If it's not a two-branch net circuit, it's a big network with a lot of branches. It becomes increasingly difficult to solve the decay time constant. You can see it will be so many. There will be so many DC part, just like this. So we have to find a way to calculate the DC component decay time. The national standard calculation standard for short circuit current in three-phase AC system. It's a Chinese national standard. It recommends the equivalent frequency model, a method to calculate the decay time constant of DC component of current. The equations is very easy. The tau is the decay time constant. The equation is like this. At first, the equivalent frequency method is proposed in this old article, and then IEEE standard, one international standard, recommend this method. At last, the Chinese national standard recommend this method to calculate the decay time constant. But it's quite different. FC means the equivalent frequency. We don't, in the normal calculation, we use the frequency of 50 Hertz. But now we change the frequency. We called the equivalent frequency. XC, it means the reactance value of the frequent self-impedance of the short circuit node at the equivalent frequency. RC is the resistance value of the equivalent self-impedance of the short circuit node at the equivalent frequency. It means we change the frequency and we create a new impedance matrix. Then we will know the impedance, the self-impedance of the fault node. Then we will calculate the decay time constant of DC component. We just need to change the equivalent frequency at first. Why we use that method? Due to the fact that the decay rate of the DC component in the short circuit current changes over time, the equivalent frequency for calculating the decay constant is selected based on the cycle. One cycle equals 20 milliseconds. What does it mean? If we want to know how fast the DC component drops at the second cycle, then we should use a new frequency. We call it equivalent frequency. The value of the new frequency is this number multiply 50. We use this new frequency to create a new impedance matrix. We can check this on the figure. The blue curve means the real current curve. Then the yellow curve means the equivalent frequency method. But we use the first time constant. It means no matter what the time it is, no matter what cycle it is, we use this parameter. We just use the frequency of this number multiply 50, and the curve look like this. But if we use all of these 4 parameters, and the curve will like the red curve, it match and fit more. So that means we divide the curve into 4 parts, and we use 4 different frequency. So after we get the AC current amplitude and the decay time, we will get the final curve of the short circuit current. It will look like this. And if we get this curve, we can do some analysis. It's quite different from simulation. Simulation will take a lot of time, but this is we call that scan, initial scan. We do the scanning to find which point, which station has the risk, and then we will do the simulation to check if the station is safe or has risk or not. Let's have some example. In this IEEE 39 system, we click the SC button. This is calculation of the short circuit current. This is our calculation conditions based on PF, means based on power flow. It means let's check the PPT. The current is calculated by these equations. VF0 means the rated voltage level of this node. But if we check this, means the voltage is calculated by power flow calculation. That means we have to click the power flow calculation button, and then it will calculate all the voltage of every node, and the CSC function will read the voltage first, then calculate. Based on IEC, if we check this, it means some certain conditions. It's a national standard condition. Static load and a motor load. There are 2 types of load. If you select any node, means you consider. If you don't select, means you ignore them. For example, in our home, the fan is belongs to the motor load. but the television or refrigerator belongs to the static load. The shunt, if you click this, means you consider the shunt on the line. The ACB means the AC line. The susceptance R means the resistance. Standard T ratio. If you select this, the T ratio is standard. If not, it's 1-to-1. It's an ideal condition. And the flexible DC system. As we know, the DC system will output some active or reactive current. If you select this, means you consider the current DC system provided. This part is load, and it's a default value. Means if I don't write the negative sequence component of the impedance of load, and it will calculate by these equations. It also calls it's also called the coefficient. And for the generator, it is also the negative sequence component of the impedance. For the AC line, this R0, X0, C0 means the zero sequence component of this parameter. If you don't write it, if the program can't read the zero sequence parameters of the line, and it will calculate the zero sequence parameter according to the positive sequence parameter automatically. And you can choose different calculate method. The voltage factor, it is the C, voltage factor. And the grounding Z means the resistance, the resistor, resistance and reactance between the fault location and the ground. Okay, let's do a simple calculation. And this page shows you two functions, single fault and the fault scan. In a single fault, you can set the fault on the bus or a branch. On the bus, there's a list of all the bus, and you can search. For example, 23. I set the fault on the new 23 node. For the branch, it will list all the branches. Branches include all the T and L card. Means all the branches are include all the line and the transformer branches. And you can set the fault location. You can set the fault in the middle of the line or the branch or the transformer branch. And there are 4 types of fault you can set, and you can set different phase. Okay. And the fault scan. Fault scan, you can choose to calculate all the node. For example, you can choose the range of the voltage. I only calculate the node belongs to the volt of 345 kilowatt. Then you can see, okay, it is very fast because the calculation principle is quite easy. You can see in this line is the short circuit current, and this line is short circuit capacity, and this is the positive, negative, and zero sequence component of the self-impedance. And you can easily see which node has the highest current. For example, we can see the new 39 has the 43 kilo n. And for the single fault, we set the fault on the new, we set the three-phase short circuit fault on the new 23. And you can see it gives the different sequence component of the fault current. It also gives the fault on the phase ABC. And it also calculate the voltage of other node. You can see the fault occurs on new 23. So new 23, the voltage is 0 because the current happened in this place. For the other, for example, the new 29, because it's way too far from the new 23. So the voltage is just be affected a little. And it can calculate the current flowing through the branch, also called branch current. In the line new 22 to new 21, you can see the current value. And in the transformer, you can see the current value. And if we, that is the example to calculate the AC current amplitude. If we want to calculate the decay time of DC component, we should select based on the international standard and then execute. So in this line, you can see the TDC means the decay time constant of the DC component of short circuit current. The bigger the number is, means the slow DC component drops. And because in this picture, if the TDC is too big, means the DC component drops slow. And as time goes by, maybe the current is still big enough. And we call this risk. And I also have an example of the CSG grid. As you can see, this is the data of CSG grid in the year of 2022. It contains all the information about China Southern Grid. Because it's a company secret, I can't send to you as a sample. So I just calculate and show you how it works. You can see for the fault scan, we can calculate different area. Guangdong area, Guangxi area, Guizhou area, and even smaller zone, smaller area. If we collect all, and we choose to calculate all the nodes belongs to the 50 belong to the 50 kilowatt, and we can see in the China Southern Grid we have 50 541 nodes belonging to the 5 500 kilowatt. If we do the simulation, we may take days or months, especially using the PSCART or some other transient simulation program. But if we do the calculation, we do the scan, and it will be very fast to give us a result, give us a reference. And we can see, for example, this station has a very big current, and we should report to the device checking department. Tell them to check and simulate all the switches and breakers in this station. It gives us a reference. We focus on the speed and the efficiency. As for the accuracy, it's acceptable. For example, we can calculate the one-phase fault. You can see it only takes about less than 10 seconds to complete all the short circuit current fault calculation of more than 400 nodes. Okay, that is all the lecture I want to. Okay, that's all.
Oh, that's all for our lectures. Do you have any question?
Oh,
Hello, my name is Alan. Mr. Two, question about uh, uh, mm, acceptance. Do you sell this program to other countries or you use only in CSG?
we just nowadays we just use this program in our country. We use in CSG and other Chinese company. We haven't used it in the foreign program.
Okay, thank you.
Thank you.
Any other question? Could you tell your camera to take a good picture?
Okay.
This is our last training. And we can see your face. Very nice picture, smile. Really thank you for your support of our program. And next we will have offline training that will be taken in China this year on October. Do you have any feedback for this training? Please let me know. And we'll also have 10 minutes to introduce
Thank you.
yourself if you like.
Thank you very much to all the team and everybody. It has been very interesting, but with very high level. Here in Ignis in Spain, we are developing a lot of renewable projects, solar and wind farms. And we are starting to know the principles of the high voltage DC current transmission. It's a very cost solution